Wonderful. Okay, so we have a very special guest at Random Adventure and a lovely backdrop here as well. We're currently at your offices in Preston. Would you like to introduce yourselves to us, please?
Yep. Hello, everybody. My name is Steff Evans, and I run a company called Evotech Computer-Aided Engineering Ltd. It's a company that specialises in engineering simulation software. So we have lots of clients that use my and our services for prototyping new designs and concepts before they're built, and it ultimately saves people lots of time and money because they can understand how something's going to perform before it gets manufactured.
So,
okay.
How did this actually come about? How did you end up
doing this?
Yes.
Yeah. Okay.
Doing this.
Right. Okay. Well, I'll give you the backstory. So I grew up in North Wales in a little town called Llangollen, which is pretty well known to lots of mountain bikers these days. When I was young, I was massively into BMX. So I got into BMX late 82, early 83. So Rad the movie came out, and not every man and his dog, but every boy and his dog wanted a BMX bike. So I got into BMX then, went through the sort of wave of where everybody was into it, and then I stuck with it after the wave fell off, so sort of into the late 80s and 90s. But I suppose that the thing that got me into what I'm doing now is that I was pretty into like maths and design and pretty creative and into sciences as well. So I did my A-levels, went to uni, and I studied mechanical engineering at uni in Nottingham. And really, and it's a bit of a cliche as an engineer, but people want to understand how things work and that sort of thing. I was really interested in why did my BMX bike break? You know, what were the driving things behind that? So studying in Nottingham, I did a placement at Raleigh in, when was it now, 94, I think it was, at Raleigh, when they had the special products division. So they were designing, manufacturing the SPD range there. I think Dynatech was the brand that they were doing, probably special products. And we had a project, or I was offered a project as part of my studies to look at a particular frame concept that had come back. So that they'd taken a sort of generic lugged frame design, and they were bringing in this sort of bonding method. So rather than brazing into the lug, they were bonding in with these sort of heated glue machine thing. And they'd switched out the tube sets from steel to titanium tube sets, and that was pretty novel at the time. And basically the tube set that they developed or they were using didn't give them the torsional stiffness in the frame. So they wanted to understand that from a product recall perspective. So I first got involved with the technology that I work with heavily now, which is called FEA, so finite element analysis, which is, in simple terms, simulation of product in a computer environment. So the way you would go about that would be you'd build the CAD models in 3D, and then you would convert it into a simulation environment, and you could then show how a product was going to perform. So in this case, we were looking at the front triangle of the frame, and the first thing was to simulate the current product, to look at the natural frequencies of vibration and the torsional stiffness. And then once you had that, we could then look at different tube sets and look at different wall thicknesses. We were limited to the OD of the tubes because they're to fit into some legacy lug stuff that we were working with, but then be able to show the influence of those changes in the virtual environment before they went anywhere near detailed drawings for manufacture and then ultimately to manufacture. So got into doing that, and then I had another project. So we did quite a lot of design and make stuff. So one particular CADCAM, so computer aided design and computer aided manufacture, CADCAM, looking into CNC development. It's pretty cool because you could basically design something in the CAD system, press a button, it would then get shipped off to the CNC machine and it would be made for you, you know, so pretty nice way of doing things. And I did again, just because I was pretty into BMX, so I developed a peg, fork, stem, head tube system before 1&1/8A headsets came in. So did that, made it, actually made 2 pairs, I sold the other pair. And that sort of got me hooked into the technology. So from doing my degree, I then went to study at Manchester University, and I did a PhD there in sort of taking the technology further and looking at what was called multi-parameter design optimization, but basically taking the simulation model of something and then using AI to predict what that optimal set of parameters would be for a given structure. So I was working with a company who were making packaging machinery, so lots of different parameters going on there. And then I came out and then I started working for a company that developed the software that we were using. So I was doing that role of sort of technical support and training role for a couple of years, probably about 3 years. And then I left and went into the aerospace industry. So that's when I really got started in using this technology in real anger on real products. So I think I did probably about 12 years on a subcontract basis in the aerospace industry. So looking at really optimal structures, so lots of civil and military aircraft development, lots of very lightweight structures, so obviously loads of composite stuff, you know, the more machined aluminium, titaniums, that kind of thing. So did that. So some the aircraft programs I worked on was the Airbus A380, the Airbus A350, getting those aircraft flying, the F-35 Joint Strike Fighter. We were doing some of the initial development work on that. Working in the aerospace industry is good, but it's a pretty long development time, and there's lots of people involved, and I never really felt like I had a hand in what, you know, the actual outcome of the final product and stuff. Yeah. And I was very removed from the product as well, you know. So did that, and then an opportunity came about where I could set myself up on my own in a sort of freelance or consultancy type basis. So I moved from working in the aerospace industry to working for myself. So I got some pretty hefty computing equipment and software licenses to allow me to do this work. And so I moved into running Evotech myself in about, well, towards the end of 2015. And I've built up a client base ever since then. And I've got lots of two-wheeled clients, so bicycle, motorcycle, lots of stuff like that. And
some you can talk about, some you can't.
Pardon me?
Some you can talk about, some you can't.
Yeah. So we talk about NDAs, non-disclosure agreements. I've got non-disclosure agreements with lots of people, but yeah, I can talk about lots of things. Okay, so yeah, that's a potted history of me from there to here, I suppose. So yeah.
Cool. So yeah, it's been a bit of a full circle for you then. Starting at Ribble, not Ribble, Valley.
Yeah.
Starting at Valley,
yeah.
And then actually then ending up working on bikes yourself.
Yeah.
Again.
Yeah.
So what kind of things, especially because a lot of bikes these days are kind of designed in the UK, quite a few.
Yeah.
And then they're actually made in the Far East.
Yeah.
So I'm guessing with you being able to actually help with the design at the beforehand, and with shipping times and everything coming from the Far East, I'm guessing that you're able to actually significantly reduce a lot of the testing, teething issues before they even actually land in a container somewhere.
Yeah, absolutely. So I work with a number of companies, or have worked with a number of companies, from sort of one-man band niche frame builders, and I'll talk specifically about some of that stuff in a bit, all the way through to some of the bigger names. Tend to be, I'd say probably 90% of them are British companies. Yeah, so it's really honing a concept and honing a design before physical prototyping or committing to a large volume order from the Far East, or just a large volume order anywhere really, you know.
Yeah.
So yeah, and that's been so I've done a lot of sort of conceptual work. So, you know, what does something look like? What are the load paths through it? You know, what's the sort of general shape it can take, all the way down to, you know, we're getting a particular machine part made for, I don't know, a mountain bike rear suspension or something like that. So very detailed look at how that's going to perform.
What the tolerance is, what's the stress load going to
Yeah,
be?
Well, stress and stiffness are a lot of the big drivers. So is it going to break? If it's not going to break, is it too heavy?
Yeah,
You know,
can we shave some weight
Yeah,
off it's still not break?
Yeah, I mean, you know, from an aerospace environment, you know, you'd get a wrist slap for something that's, you know, your shoulder's going to break, obviously, but you get a wrist slap for something that's overweight as well. Yeah. So that's a big part of what, you know, what the process is all about, really.
What are the biggest challenges with bike designs right now? Is it everybody trying to make the lightest bike possible, or?
Well, yeah, it's a big market, isn't it? So there's function and there's form, you know. So people are always playing around with those different things. I think, and we sort of talked about this before we started recording. There's a big issue in terms of the supply chain from the Far East at the moment. So there's a number of people looking at either new design development to bring manufacture back to the UK or back to a more stable environment, if you like, even if there's a bit of a higher cost, or the reverse engineering of an existing product to then understand what makes that bike work, to then do something similar back in the UK.
Right.
So that's a big. I mean, reverse engineering is again something I can talk about, but that's a big thing that we're looking at.
Yeah, you did actually share a video actually talking about reverse engineering where you were laser scanning. Was it a BMX frame?
Yeah. So I've done a number of these jobs. Two sort of smaller jobs I've done. One was with a client, a company that supplies foot pegs to the motocross teams. So sort of, I don't know. Yeah, I don't think you saw that one, did you?
I didn't see that one, but
okay.
With the magic of cinema, here is that
Here
video.
it is. Yeah. So the first one I looked at for this motocross company, or motorcycle component manufacturing company, a company called Raptor Titanium, again based in Lancashire. So they supply to pretty much all the top motocross teams and motocross riders. But their development historically was very much sort of suck it and see. We'll build something, ship it out. Does it work? Does it not work? That sort of thing. So I got introduced them through some networking stuff that I do, and they didn't have 3D CAD models of this particular design, which was challenging. So what we did through a partner company, we got access to some laser scanning technology. I don't know if laser is the correct term. They call it a blue light technology, but it's basically a sort of magic eye that sees a part and then converts that back into data. So you'll hold up the camera, or you fix the camera, and then put the part on a rotating bed, and it will rotate its way around, and the camera shines light, bounces light off the part, and builds up what we call a point cloud. So a series of points, and then once you've scanned the whole thing, those points are then brought into a CAD system, and it's a case of joining the dots, and then from that volume, if you like, you can then convert that back into a CAD model, and from the CAD model I can then build a simulation model, and we can then look at how that part is going to perform. So we can predict things like the maximum impact load that it could take, just a single load event,
or its resonant frequency and things like that as well.
Yeah, well, for loads of bike stuff and this particular thing, you've also got what we call the fatigue loading.
Yeah.
So that's a much lower level load, but it's happening hundreds of thousands of times. So you can design for those static impact loads or those impact loads or those fatigue loads. So what we're able to do there is look at ways in which we could potentially change some of the shapes to make it easy to manufacture. We are talking about the ability to maybe customize a design for someone's particular use. So you've got a very heavy rider, you can look at something versus a much lighter rider and have a sort of bespoke set of foot pegs made. So I've done that for Raptor as a client job. I've also done it as well as a sort of side thing where we've scanned it's a BMX frame, but it's representative of any frame really, where we've just shone that that optical lighting technology onto the frame, developed the point cloud, turn that into the CAD geometry, and then the simulation model, just to demonstrate that it can be done, A to B in terms of a full workflow.
Yeah.
So that's a technology that we can use for lots of things. You take an existing part, you reverse engineer it into the simulation model, and then we know what that's going to do when it's operating, and we know how to improve it as well if necessary. Okay.
So what does the future hold then? You talked about British manufacturing. Could you see that happening maybe more if you've got some UK bike companies? Would it be more kind of their higher end, lower volumes? Do you think that would be getting brought back to the UK?
Yeah, okay. So I'll give two examples of two bike companies I've worked with. One is a company called CAE, who were making 100% UK sourced and manufactured road frame. They were looking at weird and wonderful materials. So really, again, my involvement was to simulate the structure from a carbon fiber perspective. There are a lot of parameters, a lot of variables that go on with a carbon frame in terms of the number of plies and the orientation of the plies and the impact that has on the weight and the stiffness and the strength, I suppose, in terms of the impact and the fatigue loading. So we got that prototyping done, built in the UK, pretty expensive, but the manufacturing quality was really good compared with some of the Far Eastern stuff, and we chopped up a number of frames to understand what was going on in the competition, if you like.
Why do you think that it was better? Is that just lower volumes and higher QC possibly?
Yeah, so the manufacturer where this was done was an aerospace manufacturer, so they've got really good control in terms of the what we call the layup, so the way that this stuff is laid into the tool. You've got X-ray sort of checking of the frame to show there's no voids in the laminate. So really rigid and really good quality manufacturing process. So yeah, that's something that I could definitely see happening in the UK, bringing those sorts of things, maybe sort of the higher end of the market, given that there's sort of inherent costs in doing that. The other project that is probably worth talking about that I've done for a UK company is working with a guy called Tom Sturdy, who runs Sturdy Cycles. I don't know if you come across
No, it doesn't ring a bell.
No, okay. So Sturdy, again, one-man band, but he's basically looking at involving additive manufacture into the the bike or the frame development. So he's got quite a nice novel concept in the sense that he takes the knuckles or the joints, so the head tube, bottom bracket, seat tube dropouts, and he's developed those so they can be 3D printed in titanium, integrated cable routing, some of the disc brake mounting, so pretty flexible with the sort of design volume that you can work with. But for things like the tubes, which, the tube is a tube, it's a pretty efficient structure as it is, he'll buy in a tube set, titanium tube set. I don't know what his supply base is, but then he can then weld that assembly together. Really beautiful bikes. Hopefully we'll be able to show some videos of them wherever I'm pointing. And yeah, so again, that's a pretty high cost way of doing things, but it does give massive amounts of design freedom. So the potential is that you can develop different geometries and different details on that frame. There's a company in Australia, Melbourne, called Bastion. Have you seen Bastion?
I've heard of Bastion.
Yeah,
Yes.
but Bastion are doing something similar, but they're using a carbon tube. So they have titanium lugs, for want of a better term, and then the carbon tube is bonded in.
A bit like the old school Luke frames from back in the 80s? They were carbon lugs, weren't they?
Well, this is a carbon tube bonded into a metallic lug.
Yeah, that's what they were doing. The old robot, and they specialised.
Oh, were they?
Also, they used to be carbon with metal lugs as well.
Yeah. Okay. Yeah. Okay.
So it's going back to that kind of, but obviously with a bit more of a modern twist.
Yeah, but the modern take is that if you've got a parametric design, so in other words, you can feed in a rider's geometry, so rider fit profile, and maybe the riding style, and maybe the rider power. So you can predict, you can set...
If you've got somebody like me that weighs 56 kilograms, it doesn't need to be as beefy as somebody who weighs 100 kilograms.
Exactly, yeah. So, that's quite a nice, maybe a niche, bespoke element to the market as well. I suppose what would be really interesting is where those two worlds come together. So you've got, or the manufacturing costs come down, so that you're in a position where you can take a CAD and a simulation model and you can feed in the geometry and you can have your bespoke frame that doesn't cost you 10, 15k,
Yeah. That
would be a pretty nice place to get to. Carbon manufacturing is expensive. What we call the tool, so the mold, if you like, the tooling costs for carbon are pretty high, and the labour costs for getting the carbon into the tool is pretty high as well.
It's also not very green for a green sport car.
Yeah, that's true. Yeah, it's pretty nasty, isn't it? Yeah. You certainly can't get some pretty nasty chemicals in there, and you can't recycle epoxy particularly easily. I have seen some examples of people effectively sort of melting away the epoxy and then chopping up the carbon strands for then reuse. Right. But I don't think that's a major selling point in terms of the green aspects of it.
What is, well, I think two questions. First of all, you have some examples of some other work to your left.
Yeah.
And I don't know if it's worth Jake just bringing his camera a little bit closer for this, if he can do.
Okay. Yeah.
There we go.
This is a bicycle crank, would you believe? And this is a piece of work I did probably about 5 years ago now. So when additive manufacture was really starting to, well, I wouldn't say take off, but the hype was growing in terms of what you could do. I sort of took the bull by the horns and said, well, okay, let's see what we can do with this. So I worked with a partner company who were keen on demonstrating the possibilities of additive manufacture, and they developed again a printed lug titanium tube frame concept. They had it at Bespoke in Bristol.
Okay.
Yeah, a few years ago. In fact, that's where I first met them.
Whether you're uneducated, Bespoke in Bristol is it's basically a cycle show, but everything is actually kind of very cottage industry and handmade rather than your big companies that make things.
Well, actually, I first met the guys from Bastion there as well. So they're small, but they're certainly not a cottage industry because they've got very expensive 3D printers at their
I think cottage industry, but it's all more kind of bespoke made bags rather than mass produced.
The big monster companies, exactly, yeah. So this was a project that we looked at. So really looking at a bicycle crank arm, a blank piece of paper. The one thing that was somewhat limiting, and I sort of stressed this at the time, was that we were trying to work with a conventional bottom bracket. And in this case, a square taper bottom bracket. I don't even see that.
John should just hold it still for Jake just for a second.
Yeah. So it was pretty limiting in terms of the design freedom that we had. But really, what you've got with a crank arm is obviously a bottom bracket attachment or an axle attachment and then a pedal attachment. So this was really to try and look at the optimal shape that a crank arm needs to be to give it, in this case, the optimal stiffness. Mm-hmm. So for a crank arm, you've obviously got the downward load, but you've also got the torsional load. So there's a lot of twisting going on. Yeah,
because your foot isn't in line with the crank; it's off.
Yeah, exactly. So the bending load. You can work this back to engineering, sort of first principles from an engineering perspective. The bending load, the sort of in-plane bending load, gives rise to this sort of larger sort of oval shape, and then the torsional load gives rise to this sort of hollow box section. So the box section is efficient for torsion. So we did this to develop the shape, the form. We turned it into a parametric CAD model. And the interesting thing with this was that this is hollow. So there's a 1 mil wall thickness here. So I don't know if you're familiar with the 3D printing process, but basically you're melting lots and lots of layers of powder as you're printing. So there's some tiny apertures or tiny drilled holes in the pedal end here, and then literally you can just pour the material out. So what we looked at here was an optimization strategy where we could couple the power meter reading from a rider and then predict what wall thicknesses would be needed to hit a particular fatigue loading regime. So there's a number of tests, certification tests used for bikes, and this particular one, there's an ISO standard. I can't remember the numbers off the top of my head, but you have to sit the crank at 45 degrees and then fatigue test it until failure. So this was optimized for 100,000 cycles. It failed at 96,000 cycles. So in terms of fatigue loading, that's right on the on the
cusp of victory.
We predicted it, yeah. Well, we wanted it to fail at that point.
Right.
If we'd gone for 200,000, then it would be slightly heavier,
Yes,
so,
yes.
But the key thing with this is that I, through the simulation models, I've got full understanding of what this was going to do before we went anywhere near making it.
Yeah.
Hence how we could optimize it to look like this weird shape, So from a technical perspective, this worked nicely, and I spoke at loads of engineering conferences about the strategy and the process that we followed here. From a commercial perspective, total no-go. The machine that printed this, it was an EOS machine, direct laser sintering method. Is it DSM? I can't remember. The machine that printed this cost £500,000. The volume of material that we needed to print this cost 500 quid. So, you know, just from a machine and raw material setup, it would never work. But it does open the door to stuff, or to ideas and concepts when those machine costs come down, you know. Interestingly, there was a piece of work that came into the public domain a couple of weeks ago, month ago. I don't know when this is going to get broadcast, but probably early May, where SRAM showed off. Did you see that? They've shown off a 3D printed crank arm. I
didn't know.
No, so they did something recently. To be honest, with my engineer's hat on, what they've done isn't particularly great. But I think from a marketing perspective, it's quite good in the sense that they can say, you know, we could print these novel designs. You know,
we've opened the door.
Yeah, opened the door. Yeah. So I mean, you know, when I did this, there weren't any bike companies printing stuff, but now you've got Bastion in Australia, obviously shipping to a global audience. You've got Tom Sturdy doing the same. Actually, Tom's done a crankset recently, really nice looking crankset. I wasn't involved in the development of that, so I don't know what simulation was involved. So this is starting to happen from a development perspective. So, you know, if we were sitting here in 20 years' time, we'd probably all have bespoke printed parts on our bikes, you know.
Do you think that's going to be the future? Everyone's going to have a 3D printer possibly, and that's, rather than waiting for something to get shipped, you'd actually buy it.
Yeah, possibly. I mean, there is something called the hype curve that people talk about from a product development perspective. So a new technology comes in, maybe we could show a graph of the hype curve. But it's like everybody gets excited about technology, then they realize it's not really that great, and then there's a slow burn in terms of its acceptance. So that's something that could possibly come in, you know. So yeah, that's one thing that we worked on. This is something else. I've got a few bits here. These are chopped up parts of a composite frame that we developed. So that is the rear chainstay and the rear axle here, and then some sort of bonding arrangement where the seat stay comes in. We've got, actually this is a box section of the seat stay as well. Oh, sorry, chain stay. So I don't know if I'm going to grab this, but in its sort of raw form, it's pretty flexy. But when it's part of a larger frame system, it's you know, far more sort of structural integrity in there. We did some forks. I've got some forks here. So this is I'll cover up the brand. So we bought the client bought an off-the-shelf fork, and then it was sawed up. So we can see the laminate wall thicknesses. Okay.
Wow.
So there's a hollow fork, and that is actually probably more. But yeah, there's a lot of flex in there. But obviously, when that's part of a larger tube,
when it's built how it should be built,
then it's a much stronger structure. So again, this was used to help develop a laminate for an existing frame. In fact, you can see the what we call the vacuum or the positive pressure bag in here from the manufacturer. So that was left in. So this isn't a UK developed thing, but we talked about earlier about some of the quality, manufacturing quality. You know, there's some pretty ropey stuff in this development. But
we will be blurring out any brand.
What's that, sorry?
I'll be blurring out any branding.
Yeah, I'm trying to keep my hand over certain parts of this. Yeah, but yeah. So what we could do with this is just to give a head start. You could potentially scan this structure to get the digitized data, which can then go into a CAD model, and then I can convert that into a simulation model and then start to predict what the composite structure should look like. You know, where you need more plies, where you need fewer plies, ply orientations again, which I mentioned earlier. So this gave us a sort of head start in understanding. You know, if you've got a product there, then take advantage of that. So this one.
So this is as much research as it is development by taking
Yeah.
Yeah.
So again, there's the brand. I'm not going to show that, but on here we've got the micrometer marks or the micrometer readings.
Right.
To take a sort of raw thickness of the laminate.
Okay.
So from that, you've got a starting point, and then you can look at different material systems. So carbon fibre comes in many different flavours and forms. So probably have what we call a high modulus, so high strength fibre system, which could then be tailored for use in a particular way.
Whilst we're talking about carbon, not all carbon is equal, and a lot of people don't seem to, I think, appreciate that as much. You see a lot of people possibly riding around on some fake branded popular bikes that you might see on, I don't know, let's just say the podium of some big road races. What's your take on these riders and
the bikes?
And, well, more kind of the different levels of quality.
Yeah.
I think if anybody's got a good inside opinion on the different qualities in this, I think it'll be yourself, really.
Yeah. Okay. Right. So, I could talk a lot on this.
Well, how about just a concise?
Okay.
I know that's probably asking a lot.
Yeah. Okay. Well, there's a couple of things you could do. So, I think certain people you could put on let's say an expensive frame and a cheaper frame. Before we talk about, without talking about branding, certain people could have the exact same build on two different bikes and could tell the difference. Other people might not be able to tell the difference. So you've got some objectivity and some subjectivity, if you like, in there.
A bit like with cars or something as well. If you've got Lewis Hamilton, he can tell you what different engines are in the Formula One car, whereas I just drive a car. So,
exactly. So from a testing perspective, there are, again, a number of tests that you can use. And again, a lot of these are wrapped up in an ISO, international standard organisation. I think it's ISO series of tests. So you could compare two different frames for impact resistance. So for the ISO test, there's a frontal impact and a vertical impact test. There are fatigue tests. So there's a frontal fatigue, there's a pedal fatigue, there's a seat post fatigue. So riding along cobbles, say, bouncing up and down on the seat. There are stiffness-based tests that I've seen. So that there's a pretty nice test where you can clamp, if you're looking at a frame, you can clamp a frame on its side to a table by the bottom bracket, and then hang a known weight off the rear end, measure that displacement, and do the same with the fork. So that gives you an idea of the rear stiffness and the front triangle stiffness. But ultimately, as an engineer, I'd want to see the numbers. So if somebody's saying this frame is better than this frame, I'd want to know what material system's in there.
What layer of the carbon.
Yeah. So what fibre system, what epoxy or what matrix system. So that gives you your matrix. And in the aerospace industry, this goes without saying. But basically, you would have fibre in plane, tension, compression, strength and stiffness, shear stiffness. You'd have the resin stiffness, and then if you understand that, then if you know what the layup is, then you can then predict what that piece of structure is going to do. So it's pretty difficult to make subjective judgments on these things because you don't know what's in there. Yeah. But if you have the data, you can say this particular structure, and especially with the simulation model that I could develop to support this structure is going to behave in this way. So you could benchmark a frame and then say we want a stiffer frame or we want a stronger frame, or we want a better frontal torsion, or all these different things that you can play around with to predict how something's going to operate.
Okay.
Is that concise or was that long? I don't know.
I think it's as concise as I could expect from a doctor in structure. I think the other question is then, what, if you were to buy a bike, what material would you buy a bike out of? I think,
yeah.
And I think there's going to be a romantic answer and a scientific answer to this.
Yeah. There's absolutely a romantic answer. I have just bought in fact, the frame that I did the reverse engineering on, I've just bought a 2017 remake of a frame that I had in 87, so 30 years time difference. And that's a BMX frame, Harrow, you know Harrow, the brand?
Yeah.
So Harrow Master flatland frame. And it looks like a retro bike, but it absolutely isn't. It's built really nicely. It's a chromoly frame. Don't ask me what the wall thicknesses are or anything like that, but that's what we used for the reverse engineering.
Okay.
The parts that I have on that are top-notch, modern BMX parts. I haven't bought a mountain bike or a road bike for some time. I don't know. I think I do like the Bastion frames, the printed lugs with the carbon tubes.
Yeah.
And I think the ability, I mean, those guys are, I've met a couple of them. They're all, I think it's former Toyota engineers in Australia.
Right.
So they worked in the automotive industry, and that's a lot of that work's gone back to Japan. So they've taken manufacture out of Australia. So that's how they came about doing Bastion. So they like bikes, like lots of people, obviously, and they're pretty hardcore engineers. So maybe mixing some of that with my take on, well, you could potentially optimize your carbon tubes in this manner.
Yeah.
And then obviously print the lugs as well to suit a bespoke geometry as well. So yeah.
So you're sold on carbon fibre as
well. I think from a technology perspective, I think I think that the days of printing a full frame are a long way off. But being romantic, a nice steel fixed wheel bike is pretty cool as well, isn't it?
Yes. Yeah.
So got the two ends of the spectrum there, I suppose, haven't you? With a BMX stuck right in the middle.
No. Thank you so much for your time and coming down.
Oh, you're welcome. Yeah.
And showing us everything. I think that's possibly been the most condensed 45 minutes of hardcore cycling right from the very beginning. And it's very fitting, really, because I've just actually left my job in the NHS to actually work as product development. So hearing yourself talking about all of this for myself with my new kind of venture there, it's actually a really big eye-opener for myself. So thank you so much for your time.
No problem. I appreciate that.
Again, everybody, Dr. Steff Evans, thank you.
Thank you.